We have two types of systems of equations that really require our attention. So in front of us, we have 2x plus 3y is equal to 4, and 4x plus 6y is equal to 5, a system of equations. And let's analyze what the solutions to these systems look like. Now, to get started, we could take a little bit of analysis on what's going on with our A matrix and see if this guy is invertible. And if it is, we can use all the tools that we used above. The determinant of this matrix, your 2 with a 6 minus a 3 with a 4, in this case leads us to a number that is 0. And we haven't come across that yet. So because it is 0, A is not invertible. So in other words, A inverse does not exist. Now, if A is not invertible, does that mean anything? Does that have any implications on what to expect for the solutions? Do the solutions not exist? Well, let's take a look. We have other ways of dealing with this kind of problem. We could take that system of equations and augment it. So 2, 3, 4, 6, augmented with 4, 5. And we can pull out our TI-83, 84 calculators and row reduce this. All right, so if I row reduce this, I end up getting, let's see, we got a 2 by 3 matrix with a 2, 3, 4 on the first row, 4, 6, 5 in the second row, and then I'm going to do my RREF application here, and I get 1, 3 halves, 0, 0, 0, 1. Do we have solutions? Consider that in the same way that this line here, 2, 3, 4, represented the equation 2x plus 3y is equal to 4, this line here is also going to represent an equation. What equation would be represented by that last line? Well, that represents 0x plus 0y is equal to 1. 0x plus 0y is 0. And on the right-hand side, we have a 1. That doesn't make sense. We have a contradiction. A contradiction to the assumption that our system of equations has solutions. So whenever you get a contradiction like this, that 0 is equal to 1, we got a contradiction, so we have no solution here. So in this scenario, again, we got a determinant of 0, and that led us to say that led us to a problem that had no solution. Now, I want you to compare this problem to this other extra. Let's say 2x minus 3y is equal to 5, and 4x minus 6y is equal to 10. So again, I can say let A be 2, negative 3, 4, negative 6. And I can compute the determinant of this to be 2, negative 6 minus negative 3, 4. So that's negative 12 plus 12. We get another 0. So A is not invertible. Or in other words, A inverse does not exist. But as before, we could take the system of equations and try to analyze it using our calculator or Desmos. And when you plug this into your calculator and apply the RREF technique, you get 1, -3 halves, 5 halves, 0, 0, 0. For the last line here, we have that 0x plus 0y is equal to 0, which is essentially saying 0 is equal to 0. Is that a contradiction? Nope, that's not a contradiction. 0 is equal to 0. So you know what? We're good to go. This is okay to have. Very different from what we had above. Above we had 0 is equal to 1. Now that's a problem, right? So we can continue our analysis further by going to this our first row, which is telling us that 1x minus 3 over 2y, oh, came out weird, is equal to 5 over 2. So these two equations really just boil down to 1. To continue the process, I'm going to keep the x as is, but I'm going to move the 3 halves y over to the other side. And from here, I can consider the relationship between the x's and the y's to be a independent variable, dependent variable relationship. In this case, that y would be an independent variable. Sometimes called a free variable. And that x is going to be a dependent variable. Sometimes for different problems, it's convenient to take all of my independent variables and write them in terms of another variable like a t, an s, or a w. And that's what we'll do here. I'm going to say let y be equal to t. And if you're looking at the value of x, that's equal to 5 halves plus 3 halves times y, but we said that we're replacing the y with t. And by bringing in this new variable t, we have that y is in terms of t and x is in terms of t, which makes things really nice to analyze. We'll also be using this kind of idea later on to solve for the eigenvalues and eigenvectors of a matrix. So your x's and your y's can be obtained through this formula where t is any real number. So if t is equal to 1, 5, -7, 4/3, radical 3, you plug that in, I'll be able to give you values of x and y. So in fact, you have infinitely many solutions here, right? For any value of t that you give me, I can give you a corresponding x and y value. So recapping, for this particular problem, again, we had the determinant equal to 0, but unlike the last problem, this resulted in infinitely many solutions. So to recap, when you take the determinant of a matrix and that's not equal to 0, the system has only one solution. But if you take the determinant and that determinant is equal to 0, then maybe you have no solutions, or maybe you have infinitely many solutions. Okay? So this is going to be important for us to remember as we approach the next section.